Hello everyone. In this session, we will discuss about local search algorithms, tabu, local beam and ant colony optimization algorithms. Tabu search is a local search algorithm that uses heuristic search for optimization problems. So this tabu search is useful when traditional algorithms like hill climb fails. We can use this algorithm. Hill climb means hill climb algorithm generally you won't get any result when we reach a local optima. Local optima means that climber algorithm try to find the neighbors at this suppose if this is the peak of the mountain, if it reaches the highest point, then we can say that is the best solution that algorithm has found out of all possible solutions. But if it is not in a non-convex shape, there are two hills, actually this is a global optima and this is local optima, and if a algorithm stuck at local optima, then we may not get a best solution in hill climbing algorithm. So in such situations where hill climbing might get stuck, we can use this tabu search list which uses purely heuristic method. So like a regular local search algorithm, first we have to find out all the possible solution space, and we generate the neighbors, and here we maintain one tabu list, that is a memory structure that stores already previously visited solutions, so that we can avoid revisiting and avoid cyclic visiting. So sometimes a solution that is on tabu list might be revisited if it satisfies a special condition, that is called as a aspiration criteria. Now let us know how a tabu works. First we start solving giving solutions to a problem. As local search starts with a random solution, and over the time we improve that random solution, and finally we reach our goal state, that is a solution. So initially get current solution, create a candidate list of neighbors to the current solution, find the best solution from the candidate list. We maintain one tabu list. In that list, if already that solution exists, we delete, because that is forbidden. Tabu means forbidden, means already visited list, no more need to again revisit. If it is not there, we add it to the tabu list, and we stop this criteria when a sufficient solution is identified. Now let us see one problem, how tabu solve that problem. Suppose I have a problem, maximize binary vector sum. Suppose I have a binary vector 0, 1, 1, 0. What is the sum of this binary vector with n equal to, means a binary vector of 4 size, means 4 elements. Suppose 0, 1, 1, 0 is there. This is one vector with 4 size. Now what is the sum is 2, and constraint on this problem is this: there should be no consecutive ones. If there any pair, we have to pay the penalty, number of minus 0.5 into number of pairs. Here I have only one pair, so I calculate it as 1.5. Like this I find one value, fitness value for this vector. Now my objective function is find the best sequence of these 4 items of zeros and ones that has a highest score. This is indirectly it's an optimization problem, maximize this score. So how I maximize this score? If I apply a tabu search list, so initial state 1 0 1 1, that is initial sequence of, I have taken 5 n items, 0 1 0 1 0 1, its sum equal to 2. As there are no consecutives, its item, it's 2, its score is, initial score is 2. As local search algorithm, first I have to generate the neighbors as a regular local search. First I take this vector and flip first index with 1, then I get 2.5 as my score. Then second item I flipped with 0, first it's 1, now it's 0, again I get the score 1. Like this I find all neighboring states. Neighboring states, like these are all neighbors of my initial state. So out of these I got 2 sequences that maximize the scores. Actually I got 3, 2.5 to 2.5. So out of 3 I have taken 2 as the highest best neighbors who has the highest score, 1 1 0 1 0. They even though there is one consecutive, still they got it as a 2.5 scores, and initially my tabu list is 0, so I added 0 as 1. Now in these 2 I took this state as a next eligible state for exploring. Now again I go to the second iteration. Now previous this is a state that is produced by last iteration, and the tabu list is 0. Again I flip the first index with 0, again next I flip 1, next iteration I flip third one. So again I got the new scores. In this one this sequence has generated highest scores. Now this can be and this one, these 2 sequences are generated, one is 2 and 4. So in this highest score sequence is 3, so that is added to the tabu list. Earlier it is 0, now it is 4. So and I consider it as the best neighbor for exploring next solutions. Then I go to the third iteration. In third iteration, 1 1 0 1 1, I took it as a current state, and I generated neighbors of this current state as again flipping at 0 position, flipping at 1, flipping at index. So all these generated different values. Out of those, again this sequence is eligible for my next candidate list. Now this 2 is added to the tabu list. Already 0 is removed because it's already no need to again revisit it. When we have a best sequence with highest score, we forbid the old values from the tabu list, so that we can avoid cycling here in the list and no need to revisit again. So finally I got this one score with 3. This is considered as a best vector. So final result, if we do that repetitively after all iterations, we get this one best vector with the sum equal to 3, where consecutive ones are 0 and score is 3. With highest score I achieved my solution. Like this tabu search expose all possible solutions, and it maintains a memory structure that forbids already visited sequences, so that we can avoid cycles. So second algorithm, after the tabu we go for another one, local beam search algorithm. So local beam search algorithm is a local search algorithm, so where we use a beam structure. Suppose we already use this structure with estimated values and heuristic values, one structure. Now when we try to find the path in this graph that we used in A star and other one, generally we take the Initially we take 7, suppose initial state. We take one priority queue 7. From 7 I take the items with heuristic, means estimated function. Suppose there are B, C, A are neighbors of S, priority queue. So from B again I can explore B's F, H. So like this we removed items from the priority list in our previous example. But here this local beam such that rather than storing all their neighbors in the priority queue, suppose I set a beam as only 1, means item with the highest priority will be stored in the priority, and that is only for S I have A, B, C. I stored 3 items in the priority queue. But if I set beam as suppose 2, we only take the items which takes less cost to reach the items. So here what are the items? We after sorting B, C are added to the priority queue and A is removed, so that we can save time and we can stop unwanted exploration of the solutions. So local beam, so based on the beam value only those solutions are explored in local beam search. Last one here, another local search algorithm, ant colony optimization. Ant colony optimization is a probabilistic technique used to solve computational problem. So this ant colony optimization is inspired from the ants. Suppose the ants colony, suppose there are ants, they are staying in some colony, they want to grab the food. Generally ants they all go in a queue, they have a natural tendency, they all go as a group. Suppose the food, there are 2 routes from the colony, this is one short route and this is a long route. Initially one ant starts ants are there, a group of ants are in their colony, they want a food. Initially one ant starts in this direction and one ant starts in this direction. While going the ant, they release one pheromone chemical on the road. Here also this also drop some chemicals on the route. So as it is a long route, by this ant reach the food time, this pheromone chemical will wipe out, like it is dry. Whereas the shortest route, it is still it is concentrated here. After reaching ant, by smelling this chemical, again it can go back to its original colony. But the ant that comes here, it loses its smell here because it's a long distance, it evaporated. So it next this also fast. Another ant, by looking at the smell, again it goes to, so all ants make a route, this as one final shortest route by using that chemical. So the same thing we applied in our searching algorithm also. We use 2 estimation functions. One estimation function applies this logic of pheromone and tries to get the shortest route. So like this different search local search algorithms are can be applied for different real-time applications. Thank you.